So, can we start? If you're ready. I think you're muted. But good afternoon, everyone, and welcome to our ongoing SPS seminar series 2021-22, organized by the School of Basic Sciences at IIT Mumbai. The SBS seminar series conducts weekly seminar talks delivered by some of the leading experts in various scientific disciplines. It also aims to facilitate and encourage interdisciplinary collaborations and interactions, which forms a key facet of the School of Basic Sciences at IIT Mumbai. In the audience today, we have faculty from the School of Basic Sciences and faculty from the other disciplines as well. And we have PhD, Masters, and some BTech students. Today, we are honored to have with us Professor Patrick Das Gupta as a speaker. Professor Das Gupta graduated from BITS Pilani in the year 1981 with a 5-year integrated Masters in Physics degree. Thereafter, he joined the Tata Institute of Fundamental Research in Bombay and earned his doctorate in physics in the year 1989. Between 1989 and 93, he worked as a postdoc at the Inter-University Centre for Astronomy and Astrophysics, Pune, and also at the University of Wales in UK and Observatoire de Meudon in Paris. He joined the University of Delhi as a faculty member in physics in the year 93 and has been a professor at the same institute from the year 2004. His primary areas of research are general relativity, high energy astrophysics, black holes, and quantum theory. He has made several contributions in these fields and has published numerous research articles. Apart from being active in research, Professor Das Gupta is also passionate about science outreach. He likes to interact with students and has given several talks and delivered several lectures across the country on various topics of science, general physics, and astrophysics. Today, Professor Das Gupta is going to talk about early universe, black holes, and matter-antimatter asymmetry. These are topics that probably have fascinated all of us at some point of time. So we'll have the seminar for about 45 to 50 minutes, and then we can have question and answers. And Professor Das Gupta has also kindly agreed to interact with any interested students and faculty who wish to interact. So after the Q&A session, we'll have the floor open for interaction and discussion. So with these few words, I then welcome Professor Patrick Das Gupta to deliver his seminar talk. Thank you. So you're muted, I think. Can you unmute yourself?
Okay. Am I audible now?
Yes.
All right. I thank Professor Sharma for the kind introduction. It's an honor to be giving a talk to the faculty members and students of IIT Mandi. I had been here before too. I also thank Professor Verma for initiating this process and all the members of School of Basic Sciences, IIT Mandi, for this opportunity. Right. So I'm going to talk about some aspects of astroparticle cosmology that had been of interest to me for some time. And as we all know, the field of cosmology became an established field of science after Einstein propounded that gravity is simply a manifestation of the geometry of the four-dimensional space-time. And he also showed that his relativistic theory of gravity, which we today call general theory of relativity, it leads to Newtonian gravity for the case when the gravity is weak and when matter moves with speeds much less than the speed of light. In other words, Newtonian gravity follows as an approximation of general theory of relativity. In particular, the space-time curvature is brought about by the energy and momentum associated with the matter. And Einstein essentially showed that the three spatial coordinates and one time coordinates are mere labels for various events, and one can change the labels as one wishes, but the physics of the gravity and matter and space-time, the physics is unchained by the coordinate system one uses. So in particular, in Einstein's general relativity, matter, they fall due to gravity, is explained as matter simply following the geodesics in the curved space-time that is created by other matter. So in particular, Newtonian gravity would say that Earth goes around Sun because Sun's attractive gravity provides a centripetal force for the Earth to go in a bound elliptical trajectory. While from general relativity point of view, what is true is that matter like Earth or matter like Sun, the energy and momentum associated with these objects, they curve the space-time geometry around themselves, and test particles, in this case, Earth can be treated as a test particle, and the test particle simply follows a trajectory which is called geodesic, and these trajectories are essentially the extremum of the four-dimensional path. In other words, if one looks at the spatial aspect, then this trajectory is the shortest path between any 2 points in this curved space-time. So in other words, Einstein's general relativity unified gravity with the space-time geometry. Let me skip this slide. And general theory of relativity relies on the experimental observation which was first demonstrated by Galileo from his celebrated Leaning Tower of Pisa experiment, and later by many experiments like Yacht-Was, and even in our country, Ramnath Kaushik had built-in experiments at Gauribadnur Center of TIFR and so on, which demonstrated that the different objects, no matter what they are made of, they fall in gravity with the same acceleration. In other words, inertial mass is equal to gravitational mass to a great degree. And because of this, if you are in a frame of reference that falls freely in a gravitational field, you will notice that in your frame of reference, gravity simply disappears. And in fact, this was for the first time appreciated by Einstein, and he later on claimed that when he realized this, that was the happiest day of his life. So in other words, general theory of relativity, which is a relativistic theory of gravity, it rests on three physical pillars. One is the equivalence principle, because of which no matter how strong or how time dependent gravity is, in a sufficiently small frame of reference for a sufficiently small time, gravity can be made to disappear. Namely, such a frame, when it freely falls, then gravity disappears, no matter whether the gravity is time varying or varying spatially. And in particular, in such a local inertial frame, the geometry is provided by the geometry which you all learn in special relativity, namely the four-dimensional distance between two close by events is given by this object, that is c square dt square minus dx square minus dy square minus dz square, which can be written in a compactified notation where eta mu nu is the Minkowski tensor, dx nu, and mu and nu are being summed over. And in special relativity, we know that this is an invariant object no matter from which inertial frame you look at the two events. So in other words, general relativity begins by saying that in every space-time geometry, that is, in every situation of gravity, you can always choose local inertial frame where all you need to know is these two quantities. But of course, you have to also look at not just local inertial frame, but to connect one local inertial frame to another local inertial frame. Then, of course, you have to go into the full machinery of tensor calculus, and you have to use the generalized invariant proper distance between two events, so that now these coordinates are general arbitrary coordinates and the Minkowski metric has to be replaced by the general metric tensor. And the geometry is characterized by these g mu nu, which are 10 functions of space-time, because it's a symmetric g mu nu is g nu mu, and therefore there are 10 functions which describe these metric tensor. And normally x0 is denoted as time coordinate, x1, x2, x3 are the spatial coordinates. And you might ask, what tells us what metric tensor should we use? That is determined by solving the Einstein equation. Einstein equation is essentially the fundamental dynamical equation that tells how the matter determines the space-time geometry. In other words, the right-hand side of the Einstein equation has the energy and momentum tensor associated with matter, and you can see the coupling constants like capital G, which is the Newtonian gravitational constant, fourth power of the speed of light. These tell us that we are talking about a relativistic theory of gravity, while on the left-hand side, you have quantities that are purely geometrical. The RKI is the Ricci tensor, which is determined from the metric tensor g mu nu or Gij by taking second derivatives, and R is the Ricci scalar, which is simply take RKI, contract K and I, that means RII and I being summed over from 0 to 3. That will give us the Ricci scalar. And this is, of course, the Kronecker delta, four-dimensional Kronecker delta. So this is the dynamical equation called the Einstein equation that tells us how the energy and momentum associated with matter change the space-time geometry, and the space-time, non-Euclidean space-time geometry is what manifests as the gravitational field. And of course, general relativity has specific predictions or signatures. It predicts that normal matter, when they collapse, they lead to formation of horizons and singularities, and essentially such objects are called black holes. And similarly, when matter distribution changes asymmetrically, that causes ripple in the space-time geometry to propagate outwards. The ripple in the space-time geometry is what we call as gravitational waves. The other thing that emerges from general relativity very naturally are the cosmological solutions. Namely, way back in 1920s, Friedman and independently, Robertson Walker and George Lemaitre, they demonstrated that if on large scales the matter is distributed in a homogeneous and isotropic form, then by solving the Einstein equation, you get the so-called the Friedman-Lemaitre-Robertson-Walker metric. We will come to that soon. And furthermore, since general relativity, this equation is a nonlinear equation. That reason is the Ricci tensor and the Ricci scalar has quadratic terms of the metric tensor, and second derivatives of the metric tensors are also involved. So therefore, the Einstein equations are highly nonlinear and very few exact solutions are there. In particular, there is so far no exact dynamical two-body solution in general relativity, although numerical relativity has been exploring that when two bodies they are under gravitational forces alone, what kind of geometrical ripples that go about, but no exact solution. So one expects that there are still a lot of surprises that can emerge in future, new exact solutions. Right, now as I said that whenever matter distribution is homogeneous and isotropic, then there is the Robertson-Walker obtained a general form of the space-time geometry. So if the matter is distributed in a homogeneous and isotropic form, this is the form of the geometry. But note, there is a function a of t. Here the square of a of t appears, and there is a constant k which also appears. This constant k represents the curvature of the three-dimensional subspace. So k can be +1, k can be -1, or k can be 0. +1 tells us about a closed universe because R can only take values from 0 to 1 because k is +1, otherwise 1 minus r square will become different. We know 1 minus r square better be positive. While k equal to -1 and k equal to 0, they are called open and flat, spatially flat universe respectively. And when one plugs in this form of geometry in the Einstein equation, then one gets the so-called Friedman-Lemaitre equation. A note that in this slide, I've also retained a term, a constant times the metric tensor. This is a so-called cosmological constant term that was originally proposed by Einstein because he wanted a static space-time geometry. He thought that the universe doesn't change with time, so he wanted to get a static solution, and he noticed that he cannot get a static solution if there is no such term. So he introduced a cosmic repulsion term and got a static solution, but it was unstable. But soon in 1929, Hubble, through his astronomical observations, showed that the universe is not static. Rather, the distances between galaxies change with time. And then Einstein realized what a blunder it was. He could have, without introducing this cosmological constant term, he could have in fact predicted that the universe is not static, but universe is changing. And before Hubble discovered it using astronomical tools, and that's why Einstein always called his introduction of this cosmological constant term a blunder. But today we know that this blunder has come back to cosmology because observation tells us that today the distance between galaxies, it is not only increasing, but the rate at which it is increasing is also increasing with time. That means today our universe is expanding at an accelerated rate, and this late time acceleration requires a repulsive kind of gravity, which can be also obtained using the so-called Einstein's blunder, namely using a cosmological constant term. Of course, there is a problem, the so-called fine-tuning problem associated with cosmological constant. That is one of the outstanding problem in today's fundamental physics, the so-called fine-tuning problem, because the quantum vacuum also behaves like a cosmological constant. So therefore, the quantum vacuum will appear on the right-hand side, while there'll be Einstein's cosmological constant on the left-hand side. And today's observations show that there's a near cancellation of the quantum vacuum term and the bare cosmological constant term, so that there is a remnant of net cosmological constant there, so that it can explain the late time acceleration. But why both terms should cancel to such a degree is a fine-tuning problem, and many physicists are still trying to solve this cosmological constant problem. Right, but note that this unknown function a of t that appears in the Robertson-Walker line element for the space-time geometry, through Einstein equation, one gets this Friedmann equation, and by solving this, one can get the time dependence of this scale factor that tells us about the expansion. So pictorially, what we see is that if you take galaxies on large scale, then the distance between galaxies is increasing, because this a of t is increasing with time. And because a of t determines the spatial distance between two different points, if a of t increases with time, then it can explain the increasing distance between the galaxies on large scale, which is what was observationally discovered for the first time by Edwin Hubble. And therefore, it was immediately realized that if you run the whole process backwards, that means in the past, galaxies were close by. If you go further back, they were all top of each other. Further back, they were all gaseous matter. Further back, they were dense and hot. So Hubble's observation gave a thorough and solid observational key that our universe in the past was dense and hot. And today, our model of the universe is this, that when the universe was only 10 raised to the power minus 44 to minus 43 seconds old, then of course we can't use Einstein's general relativity, because that is the Planck era, because the Planck time is 10 raised to the power minus 44 second, which tells us that that is the realm of quantum gravity. But after 10 raised to the power minus 43 seconds onwards, one can use classical general relativity and the particle physics model. And when the universe was between 10 raised to the power minus 38 to 10 raised to the power minus 33 seconds, it is the grand unified theory era, because grand unified theory, they are associated with phase transition at very high temperature. At this time, the universe, the temperature of the universe was about 10 raised to the power 29 degree Kelvin, or in energy unit, because Boltzmann constant K into T has the energy unit. So roughly 10 to the power 4 degree Kelvin corresponds to 1 electron volt. And during the grand unified theory era, when the corresponding phase transition means the weak forces, electromagnetic forces, as well as strong forces, all were all unified, and hence the grand unified theory. And such a unification was brought when the typical center of mass energy between particles is more than 10 to the power 16 GeV. And universe indeed was so hot, namely more than 10 to the power 29 degree Kelvin, so that at this point all the forces were unified. But since the universe is expanding, universe is also cooling, so there was a series of phase transition around when the universe was between 10 to the power 11 minus 11 to 10 to the power minus 10 second. There was another phase transition, the so-called electroweak phase transition, when weak interaction and electromagnetic interaction separated. Then there is also another phase transition when the universe cooled to about 150 mega electron volt. Then there was QCD phase transition, so that the quark gluon soup, there was a phase transition, and you had hadronic phase transition. That means the strong interaction underwent a phase transition, so that you had quarks combining to form hadrons like protons, neutrons, and other forms of nuclei, light nuclei. And then universe, when it cooled below few thousand degree Kelvin, then electrons combined with protons to form atoms, helium and hydrogen atoms were formed. Further cooling led to neutral atoms through their self-gravity becoming stars and galaxies. And we are now in a Milky Way galaxy on a planet, and all these have formed because of various phase transitions in the early universe. So this is a brief summary of early universe cosmology. And as I said, that today the so-called observation of type 1a supernovae, for which Rice, Schmidt and Perlmutter were awarded Nobel Prize around 2012, from the observations, now most cosmologists, they believe that our universe at the moment is undergoing an accelerated expansion, and that can be brought about only if there is some kind of a strange matter which causes repulsive gravity. It can of course be explained by cosmological constant, and in fact the observations today say that whatever that exotic matter is, the so-called dark energy, its equation of state is very close to what one would have if it was due to cosmological constant. So cosmological constant is still the favored explanation for the late time accelerating universe. Right. Now, as I said, that universe, therefore, our standard Big Bang model is a model that tells us that in the past, the universe was extremely hot. As you can see, that the universe in degrees Kelvin, the kind of temperature you have, and as the universe expanded, that means as one universe became older and older, the temperature fell, and at various times, various phase transitions kept on happening. So this slide is a cartoon that tells us at what time, what particle physics were relevant. And of course, the grand unified theory matter, in the grand unified scales, the leptons, like electrons, neutrinos, quarks, they were described by the same multiplet, the gauge group multiplet. But then after the gut phase transition, okay, somewhere around this time, the quarks and the leptons, they separated because the strong interaction is mediated only by quarks, while um, quarks enjoy, of course, both electromagnetic forces as well as weak forces, but the leptons enjoy only weak and electromagnetic forces. Of course, gravity is universal because gravity is sourced by energy and momentum, and all objects have energy and momentum. Therefore, gravity is universal as predicted from general theory of relativity. Now, note that because the universe was very hot and dense in the past, Stephen Hawking had pointed out that in the past, therefore, different causally connected region. Note that in the past, when the universe was very young, since speed of light is finite, only smaller regions will be in causal connection with each other. For instance, if the universe is 10 to the power minus 35 seconds old, then maximum distance light could have traveled is 10 to the power minus 35 second into 3 into 10 to the power 10 centimeters per second. That makes it 3 into 10 to the power minus 25 centimeter. So in other words, when the universe was 10 to the power minus 35 seconds old, the entire universe, only small pockets were causally connected to each other. That means a particle would see only this much of the region, which is a region of size 3 into 10 to the power minus 25 centimeter. The other regions will be totally, these particles will be unaware and oblivious of what is going on outside the sphere. And that is true about all other causally connected regions too. But what Hawking had argued, that because it was dense, universe was so dense at that time, any tiny fluctuation, the space-time geometry fluctuation or density fluctuation, could make this different causally connected region collapse gravitationally to form black holes. Such black holes, because they were not formed due to stars, such black holes are called primordial black hole. Later on, Hawking and Carr, they showed how generic are formation of primordial black hole in the past. So, as you can see, early universe, till now I was talking about mostly the particle physics that dominated early universe, but then Hawking and Carr, they showed that because of the possibility of formation of primordial black holes in different causally connected region in the early universe, even gravitational physics, after all, black holes are pure gravitational objects, even black holes would play an important dynamical role in the early universe too. Yeah. Now we come to the so-called matter and antimatter symmetry. We all know from astronomical observations that on large scales, the universe is essentially matter dominated. What do I mean by matter dominated? That universe is made out of baryons like protons, neutrons, and electrons. On large scales, you don't see antimatter like those which are made of antiprotons, antineutrons, and positrons. And what are the various observational constraints? Why do we say that our universe is on large scales made out of matter and not antimatter. Suppose you have galaxies, and suppose there are anti-galaxies too, but galaxies are not pure island. Galaxies have diffused matter around them. Anti-galaxies would have diffused antimatter around them. And this diffuse matter around galaxies and diffuse antimatter around anti-galaxies, they will certainly have interfaces where they meet. And we all know when matter and antimatter meet, they give rise to annihilation, resulting in gamma photons, because when you annihilate a positron with an electron, the net production of energy, the minimum production of energy is about 1 MeV. That means you will have two gamma photons, 0.511 MeV each. And proton antiproton annihilation will give rise to gamma photons of the order of 940 MeV, close to 1 GeV gamma photons. And therefore, we know if there are large scale antimatter present, we should be seeing a diffuse gamma ray background, but such gamma ray background has not been observed, telling us that in our observable part of the universe, galaxies are made of matter alone. The only antimatter that we observe are secondary antimatter particles that we observe in cosmic rays. Like cosmic rays, we have a very tiny fraction of antiprotons, positron, and they are generated by secondary processes. So therefore, the question naturally arises that why is it that our universe is matter dominated? Now, the thing is that there is also another observation, because at some point when neutral atoms were formed, the photons, they got decoupled from the matter, because photons don't interact much with neutral particles. And this decoupled photons, they were in a serendipitous manner observed, okay, the so-called decoupled photons are observed today, and it was first time observed by two microwave engineers, Wilson and Penzias. For that, they were given the Nobel Prize in 1965, the so-called cosmic microwave background. And cosmic microwave background tells us that for every baryon, that means for every proton, there are about 10 to the power 10 photons. So therefore, there is a ratio, the so-called net baryon to photon ratio, and that is close to 10 to the power 10. That immediately gives us a clue that probably early in the universe, matter and antimatter, they were of more or less equal in number. In fact, if for every 10 to the power 10 antiproton, if there is 10 to the power 10 plus 1 protons, then they would annihilate and 1 proton would remain, and there'll be 10 to the power 10 photons. So the fact that the baryon to photon ratio is 10 to the power 10 suggests that universe probably began with equal number of baryons and antibaryons, and then when they underwent an annihilation, if there is a slight excess of baryons, that is what will remain and make the observed matter-dominated universe. And the remnant of, that is after the whole of annihilation, the remaining quarks, not the antiquarks, but the remaining quarks would give rise to protons, neutrons. They will form deuterium, helium, and other light elements. Of course, more complex elements with higher atomic number were not synthesized in the early universe, but they were synthesized in the cores of stars. Right. So if one doesn't want a fine tuning, after all, there is no reason why universe would have been born with a fine tuned baryon to antibaryon ratio. That is, for every 10 to the power 10 antibaryon, there is 1 plus 10 to the power 10 baryons. If we don't want such a finely tuned beginning of the universe, and the symmetry considerations would tell us that when the universe was born, right around the time of the Big Bang, the number of baryons was exactly equal to number of antibaryons, and also number of leptons were exactly equal to the number of antileptons. Then there must be some process by which an excess baryon was created, so that today we live in a universe that is dominated by matter. That means matter that is made of baryons and electrons. Okay. Now the question is, how do we have the situation where equal amount of baryons and antibaryons annihilated, yet one had an excess baryon? Okay. That means, how do we have baryogenesis? And this is still a problem in which lot of physicists are working, the so-called problem of baryogenesis. And one particular way that was suggested as to how to have baryogenesis, when to begin with, one started with a universe that had equal amount of matter and antimatter. So Sakharov in 1967 published a paper where he laid down 3 conditions to generate excess baryons when the universe, to begin with, started purely in a symmetric manner. That means equal amount of matter and equal amount of antimatter. And the 3 conditions to have excess baryon is, first of all, the particle physics models must have in it baryon number violating processes. The second condition, that is obvious, because if you want to generate net baryons, given that the universe began with equal number of baryon and antibaryons, one must have processes that violate baryon number. The second criteria is that physical interactions must violate charge conjugation and charge conjugation times parity. These 2 symmetries must be violated. See, matter and antimatter, they are linked to each other by this charge conjugation operator. So when you take as you know, in quantum theory, everything is determined by the so-called state vector belonging to the Hilbert space. So matter state vector, when you apply the charge conjugation operator, the resulting state vector corresponds to antimatter. And obviously, if you want to generate an excess matter over antimatter, given that initially they were exactly identical in number, you need to violate the charge conjugation symmetry, because charge conjugation symmetry is a symmetry between matter and antimatter, and therefore you have to, some processes must violate charge conjugation symmetry. Only then you can have excess matter over antimatter. And similarly, charge conjugation operator times the parity operator should also be violated, because the baryon number operator is an operator that is odd under the CP operator. That means baryon operator, if you hit on one side CP and hit on the other side CP inverse, then the baryon operator changes its sign. So in order that you, starting with net baryon number 0, if you want to have a non-zero net baryon number, the CP symmetry should also be violated. And because in quantum field theory CPT is an exact symmetry, CP violation also means that at least for baryon number generation processes, time reversal should also be violated. The other condition that is required is that there must be processes which happen very far from thermodynamic equilibrium. That means a net baryogenesis or a net matter can be obtained only when there is departure from thermodynamic equilibrium. Why is it so? Because even if the first two conditions are met, if there is thermodynamic equilibrium, then we know for every processes that generate a net baryon number, there's also a process that generate the reverse. That means a net negative baryon number, because when there is thermodynamic equilibrium, if A plus B is C plus D, then C plus D also becomes A plus B, and both the rates are equal when there is thermodynamic equilibrium. So therefore, in order to generate a net baryon number, these processes must happen far from thermodynamic equilibrium situation. So there should be departure from thermodynamic equilibrium. So these three conditions are necessary to produce excess matter over antimatter. So now I have essentially laid down the problem and what kind of conditions the solution must satisfy. All right. So in particular, there are various baryogenesis model like grand unified theory baryogenesis or electroweak baryogenesis. There are different scenarios portrayed. We also, of course, today we don't know which processes are really useful for the observed baryogenesis. But in grand unified theory, there is the so-called X boson, which can undergo the following kind of decay. Remember, we are talking now about grand unified theory, which is a theory that unifies electroweak forces with strong forces. And as I said, strong forces today are experienced only by quarks. But during the grand unified theory era, there was only one kind of force, and therefore quarks and leptons both enjoyed that kind of force. So therefore, the grand unified boson, X boson, it can decay into two quarks. And as you know, if you take a quark like U quark or D quark, each quark is associated with a baryon number 1/3. So when the X boson decays to two quarks, there is a baryon number violation. You get net baryon 2/3. But of course, X bar, the anti-X boson, it would decay into Q bar, and the baryon number generated will be -2/3. And therefore, when there is thermodynamic equilibrium, then equal number of X and X bar will decay. So there is no net baryon number generated. Similarly, X boson can go to an antiquark and an anti-lepton, like it can produce an anti-U quark and anti-electron, okay? And then the baryon number violation is -13 because leptons don't carry baryon number, okay? So therefore, in granified theory baryogenesis, one uses the decay of X and anti-X, that is X and X bar, to generate the excess baryons. Today, in the remaining time, what I will do is I will describe the work that we have been undergoing, namely the
Sir, you are muted.
yeah, sorry, am I audible now?
Yes, sir.
Yeah. No, there was a call, and because I'm using my cell phone for internet, so I got muted. Yeah, okay. Uh, uh, yeah. So, am I fully audible now?
Yes, sir.
Yeah, very good. Uh, yeah. Okay. So, therefore, from now on, I will talk about the work which we are involved in, namely how to generate baryons or net matter from black holes. And black holes, I'll skip the slide because we know that black holes are objects in which the self-gravity of matter causes matter to shrink. That means the density becomes so large that matter shrinks within a size less than the so-called the gravitational radius. So for a symmetric collapse, the gravitational radius is given by the Schwarzschild radius. So if a symmetric distribution of matter of mass m collapses to a size less than 2 gm by c square, then general relativity tells us that nothing can halt the collapse, and the entire matter will just keep collapsing and go into a point. And the fact that entire matter goes into a point means that the density becomes infinity. The geometrical quantity like radius of curvature goes to 0. The Riemann curvature tensor, each component goes to infinity, and therefore you have a singularity. And there is a mathematical surface, spherical surface of this radius 2 gm by c square called the event horizon, covers this space-time singularity. And this event horizon surface is such that any event happening below the event horizon surface can never be seen by an external observer. And soon, in 1963, another black hole solution was discovered by Roy Kerr, corresponding to rotating black hole. If there are questions, I will come to various kind of black hole, but because I am the time is limited, I'll rather say that uh, the uh, the fact that the black holes are a natural consequence came from the first idea came from Chandrasekhar. Earlier, it was thought that black holes are simply mathematical solution, but Chandrasekhar showed that when a star is more massive than a particular threshold, one cannot halt the gravitational collapse. And then, based on an equation developed by Amal Kumar Raichaudhuri, the so-called Raichaudhuri equation, Penrose and Hawking proved powerful theorems saying that for normal matter, when there is gravitational collapse, they lead to formation of singularities and black holes. And we all know that the discovery of supermassive black holes also fetched Nobel Prize last year. So Penrose, Reinhard, and Andrea, they all received Nobel Prize last year for the evidence for supermassive black hole. And of course, theoretically, Penrose had proved powerful theorems. Of course, Hawking, unfortunately, is no more, so only Penrose got the award. But let me now, if there are questions, I'll come back to all these. But let me go to the properties of the so-called black holes. One is that the classical general relativity showed that if you take two black holes and combine them, or you take matter and make it fall onto the black hole, there is a property, unique property for these black hole processes, namely the area of the event horizon always increases. That means if you take two black holes, this has an area of the event horizon, this also has another area of the event horizon, but when they combine, they form a bigger black hole, and the resulting event horizon area is more than the sum of the event horizon areas. And it was shown by rigorous mathematical argument that in classical general relativity, one cannot decrease the area of the event horizon. Okay? And this led to the so-called black hole thermodynamics. So we know the usual laws of thermodynamics. The zeroth law is that for a system in thermodynamic equilibrium, temperature everywhere is same. Similarly, for a black hole, the surface gravity anywhere on the event horizon is identical. And the first law tells us that differential in the internal energy is equal to temperature times differential in entropy plus PDV and other terms. Similarly, for a black hole, it was shown that for any process, the change in the mass of the black hole is proportional to the change in the event horizon area, with the proportional constant given by something proportional to the surface gravity. And there'll be other terms related to angular momentum of the black hole, angular velocity of the black hole, and so on. And just like our second law of thermodynamics tells us that change in the, there is a typographical error, it should be S. That means change in the entropy is always greater than or equal to 0. Similarly, for black hole thermodynamics, in any process, the event horizon area always increases. Okay. And similarly, there's a third law which says that in finite number of steps, one cannot cool a system to absolute zero. That means temperature can never be zero in finite number of steps. Similarly, in the case of black hole, one can show that in finite number of steps, you can't make the surface gravity equal to 0. One moment, I think in my hotel room, there is some visitor. I will just come back. One moment. One moment. So I'm sorry about it. I'll have to pause and and I'll come back. Okay, one moment. Yeah, am I audible? Hello?
Yes, yes.
Yeah, yeah. Sorry about it. I had a visitor. So, yeah, yeah. Yeah, so as I say, so saying that the surface gravity, one cannot decrease it to zero in finite number of steps because surface gravity on the event horizon becomes zero only for a black hole of infinite mass. And that cannot be achieved in finite number of steps. Now, there is an interesting history associated with it. Bekenstein kept on claiming that the area of the event horizon is truly the entropy, actual thermodynamic entropy of a black hole. And Hawking was irritated by it because Hawking's idea was that after all, black hole doesn't have any radiation emerging from it, unlike in the case of thermodynamic system. So why should there be a real correspondence between event horizon area and the thermodynamic entropy? So he wanted to prove Bekenstein wrong, but he ended up proving Bekenstein right. So when Hawking started considering the quantum effects near the event horizon of a black hole, he found that indeed the event horizon of a black hole appears like a black body, and the temperature of the event horizon is given by this expression. Note that this expression has the reduced Planck's constant, speed of light, Newton's gravitational constant, as well as the Boltzmann constant. So it's a formula which has quantum physics, relativity, and gravity as well as thermodynamics. All right. And of course, the work itself is based on semi-classical quantum field theory in the background of the classical general relativistic solution of a black hole. But it can be understood as, after all, quantum field theory tells us that the quantum vacuum is not a trivial thing. There, in the quantum vacuum, virtual particles are created, like a virtual pair of positron and electron will be created, virtual pair of photons will be created. And so therefore, sometimes what can happen is that when such virtual particles are created in the quantum vacuum, one of the particles can go into the event horizon, but then they can't again recombine. So therefore, the other particle escapes as a free particle. And this is what appears as the so-called Hawking radiation. And of course, this happens at very small time scales in accordance with energy energy time uncertainty principle of quantum theory. In other words, an electron and positron gets created spontaneously from vacuum, only they survive only for about 10 to the power minus 35 seconds, because the electron mass and positron mass, they are identical. 2 mc square times 10 to the power minus 35 is exactly Planck's constant divided by 4 pi. So in other words, the The Hawking radiation can be thought of as the fact that whenever such spontaneously created pairs from vacuum emerge, one of the particles enter the event horizon so that the other particle escapes. Okay, and therefore, because such processes are so rare, the Hawking radiation, which is essentially a quantum process, is not very substantial that you can observe it from astrophysical black hole. Let me skip all these. If there are questions, I will come back to all that. I will also skip this slide because this tells us in a quantitative way how primordial black holes are formed. Basic idea is very simple, that you take the expanding universe and take the causally connected region, and because the density of the universe times the volume of the causally connected region is the total mass, if there is an excess mass such that the Schwarzschild radius, okay, is bigger than the causally connected region, it will simply collapse into black hole. That is the simple physics that goes in for the formation of supermassive black hole. And now, as I said, the Hawking temperature is given by this equation, and in numerical terms, you put in the values of various constants like kb, h bar, g, etc., you will find that the numerical value of Hawking temperature is that if you take a black hole of mass 1 gram, then the corresponding temperature of the event horizon is 10 to the power 26 degree Kelvin. And because 10 to the power 4 degree Kelvin is equivalent to 1 electron volt, so 10 to the power 26 degree Kelvin corresponds to 10 to the power 13 giga electron volt. And if the mass of the black hole is very large, then the temperature drops, because the Hawking temperature is inversely proportional to mass of the black hole. So if you take a sun-like black hole, as you know, sun's mass is 2 into 10 to the power 33 grams. You plug in this value in the denominator, 2 into 10 to the power 33 gram, you will get temperature to be 0.5 into 10 to the power minus 7 degree Kelvin. That is a very, very tiny temperature, and therefore astrophysical black holes, their Hawking temperature is too low to be detected. On the other hand, we talked about primordial black holes, and in particular, although I skipped the slide, that when the universe was 10 to the minus 35 seconds, then the causally connected region was so tiny that the total mass within that causally connected region is about 2 kilogram, that is 2000 gram. So a gut scale, a primordial black hole that was created during granidified theory would weigh about 2 into 10 to the power 3 grams. Okay, and 2 into 10 to the power 3 gram, the Hawking temperature, if you plug in the value in this formula, if you put the mass to be 2000 gram, then you will get 0.5 into 10 to the power 23 degree Kelvin. That is a high temperature. So in terms of GeV, if you put mass to be 2000 grams, then you will get 0.5 into 10 to the power 10 giga electron volt. Okay, very high energy particles would be radiated. So in other words, if you have a primordial black hole of mass 0.001 gram, that is 10 to the power minus 3 gram, its temperature would be, one moment, I'm extremely sorry. Okay, now it's all right. The phone call has stopped. One moment. Someone is trying to call me. Yeah, please excuse me. I'll just excuse me. I'll just answer the call. Sorry about it. Uh, I'm in a hotel in Dubai, and because of which there is some disturbance. Or am I audible now?
Yes, yes,
Yeah, yeah.
yes.
Sorry about this. There's some disturbance from the hotel, and they want something or other. One moment. Yeah. Right. So let me go to the slides. Yes. So as I was saying that when you have a primordial black hole of mass 0.001 gram, then the corresponding temperature, if you plug in into the formula, the temperature of the event horizon will be 10 to the power 16 GeV. Okay. And clearly, that means such a black hole would be predominantly emitting the gut scale X bosons. Okay. And that is basically the idea that we have used in our work. So this is a brief procedure for baryogenesis in our work. So you have gut scale black holes, which are about 1,000 grams or so, and they evaporate due to Hawking radiation. And when their mass becomes 10 to the power minus 3 gram or less, because as they emit Hawking radiation, their mass also goes down, then the Hawking temperature rises. When the mass falls below 0.001 gram, they rise to more than 10 to the power 16 GeV. And at that point, therefore, the primordial black holes essentially emit the X bosons and X bar bosons, the antiparticles, and decay of these would give rise to the net baryons, and therefore you'd have baryogenesis, because these X bosons and X bar bosons that are emitted from the black holes, they would satisfy all the three conditions: baryon number violation, C and CP violation, as well as out of thermodynamic equilibrium condition. But I must point out that there are two major uncertainties in the scenario that we have outlined in our work. And the uncertainty is, what is the fraction of matter that become primordial black hole during the grand unified era? And similarly, our work shows that if the CP violation, the dimensionless CP violation parameter, is about 10 to the power minus 4, then we could explain the observed baryon to photon ratio. But one is not sure, because it's a free parameter. One doesn't know in the grand unified theory what kind of CP violation parameter is expected. So therefore, these are the two issues that have to be sorted out till we zero in as to what is the real reason we have our universe to be having a net matter. Okay. And those who are interested, you can look at these work, which essentially talks about how to have baryogenesis from evaporating black holes that survive. These black holes which are formed, they survive beyond the electroweak phase transition, and when their mass becomes as low as 0.001 gram, they cause the net baryogenesis. There are many things I wanted to sort of talk about, but I think what I will do is I'll stop at this slide. I would point out that the Hawking result, which unifies three different fields. One is thermodynamics, the other is gravity, and the third is quantum. So the Hawking temperature brings one to a situation where theoretical physicists think that it is saying something fundamental about quantum systems, thermodynamic systems, and general relativistic system. And most workers who work in the field of quantum gravity, they think that at some fundamental quantum gravity domain, these three areas of physics will get unified. I'll stop here. It is more important that we have interactions and questions. Thank you very much.
Thank you very much, Professor. I think, yeah, this was a very, very interesting talk, and I'm sure all of us learned a lot. So let's start. We can have now questions and interactions. So I see there's a question on the chat box. I'll just read it up.
Yeah.
So there is a holy
So
cow
please don't
collaboration.
hesitate.
Yeah,
Any
so-
questions you have, please feel free to ask.
So Aruna is asking if there's a holy cow collaboration in Germany who measured the H naught value, which is less than the current known value of H naught, and they have used gravitational lensing method. So if this discrepancy is proved correct, then what can we expect in terms of new physics?
Yeah, so you're talking about the Hubble parameter, right? So there is, I had shown, although I didn't discuss the situation, but yeah, I had mentioned about the tension in the Hubble parameter. Yeah, so this is for the rest of the audience members. As you know, the Hubble parameter H naught, if one considers the cosmic microwave background, the value is close to 67 kilometers per second per megaparsec, while measurement of Hubble parameter using nearby galaxies is substantially larger. It is 74 kilometers per second per megaparsec. And so therefore, if this is indeed true, again, the question is that on both the values, there are sufficient error bars, and the error bars almost cause both of the values to overlap. But suppose we say that these two values are indeed, we can take it, okay, as really measured quantities, then there is scope for new physics, because then it would mean that something happened in the present day universe, because nearby galaxies means we are talking about the present day universe, while the Hubble parameter estimated from cosmic microwave background radiation, the physics that goes into it, the physics is when the universe was 380,000 years old. That means much younger than the present age, which is 14 billion years. So therefore, if these two values are indeed the correctly measured values, then the new physics would tell us that the current accelerating expansion of the universe may have something to do with a large value of the Hubble parameter, or as with one of my students I had speculated, the work is still not completed. We had suggested that probably sterile neutrinos, they cause repulsive gravity, and neutrinos being produced copiously from stars, the present day universe would have much larger number of neutrinos than the neutrinos that populated the universe when photons decoupled from the rest of the matter. So could it be that the repulsive sterile neutrino causes a greater expansion rate, and that's why you have larger value of the Hubble parameter. So it is a very interesting area of research now. And indeed, if there is such a large discrepancy in the measurement of Hubble parameter, probably there is new physics involved.
Okay, thank you, Professor. So Sankalp has two questions. Is there a limit on mass of primordial black holes? And the second question is, as primordial black holes are non-baryonic, can they be possible candidates for dark matter?
Yeah, so that's a very good question. So as you can see that the mass of the primordial black hole is related to at what time the black hole was created. So larger is the age of the universe, bigger is the mass of the primordial black hole. So in other words, if t is much smaller than 10 to the minus 35 seconds, so let's say if t is 10 to the minus 40 seconds, okay, then the mass of the black hole is even tinier. It will be 2 into 10 to the power 3 multiplied by 10 to the power minus 5. So 2 into 10 to the power minus 2 gram. So, but we also know that all these analysis can be done only up to t equal to 10 to the power minus 43 second. Because less than t equal to 10 to the power minus 43 second, we don't know what is the correct theory of gravity. So this formula can be believed only up to or till t is 10 to the power minus 43 second. So probably we can say that the primordial black hole analysis is valid only for time greater than 10 to the power minus 43 second, and hence the lowest mass black hole will be 2 into 10 to the power 3, 10 to the power minus 43 by 10 to the power minus 35, that is 10 to the power minus 8. So therefore, 2 into 10 to the power minus 5 gram. So we can be certain that primordial black holes of mass as low as 2 into 10 to the power minus 5 gram could have been created. But when the universe was even younger than that, we cannot make these arguments because general theory of relativity will not be valid for t less than 10 to the power minus 23 second. Sorry, I forgot what was the second question.
So that was, can they be candidates for dark matter?
Primordial black holes?
Yes.
Yes. In fact, it's very interesting that you asked this question because many dark matter researchers believe that primordial black holes, which weigh between 10 to the power 20 and 10 to the power 21 gram, could form dark matter candidates because this window, 10 to the power 20 to 10 to the power 21 gram heavy primordial black holes, they have not been constrained by other observations. So indeed, dark matter could be composed of primordial black holes whose mass lie between 10 to the power 20 and 10 to the power 21 gram.
So there's another question by Robin that in starting slide, we have seen various phase transition during the inflation period. So, and we know that during phase transition, there is always some deformation. So is there any deformation structure in the universe? And if so, what are its properties?
Yeah, so not deformation. What you probably mean is the change in the order parameter. As you know, in statistical physics, a phase transition is described by an order parameter. For example, take the phase transition of water, liquid water becoming steam when you heat it. So in this case, the order parameter is the number density of water molecule. So when you have liquid water, the number density of water molecule is very large compared to when you have the steam state. Similarly, if you take the supercooled helium, the so-called superfluid helium, that is also a phase transition where the order parameter is roughly the wave function condensate, because helium is bosonic, and when the helium atoms they form a Bose-Einstein condensate, they become superfluid. So it is the condensate wave function that acts as the order parameter. So every phase transition is associated with the change in the nature of the order parameter. So you're right. So for example, if you take the phase transition of electroweak phase transition, then the electroweak phase transition, you can think of the order parameter to be the mass of the quarks and the mass of the leptons. So you know that before the electroweak phase transition, the leptons were having zero rest mass, and so did the quarks. Quarks too had the rest mass to be zero. That's because the vacuum expectation value of the Higgs field was zero before the electroweak phase transition. While after the electroweak phase transition, the Higgs field acquired a non-zero vacuum expectation value, and thereby all particles got their rest masses. So therefore, it is the vacuum expectation value of the Higgs field that can be taken as the order parameter for the electroweak phase transition. Similarly, in the case of the QCD phase transition, in the QCD phase transition, quarks and gluons, they undergo a change in the phase in which the baryon numbers are chiefly in the form of hadrons. That means in the quark-gluon phase, the color quantum numbers, particles had color quantum numbers were non-zero. But once hadrons formed, hadrons have zero color quantum number, because for every quark, there is an anti-quark. For example, take proton. Proton is made out of UUD, and the three colors, they reside in equal numbers. The red, green, and blue colors, when they have equal number of colors, the net color is zero. So therefore, when QCD phase transition happened, from non-zero net color quantum number, you went to zero net color quantum number. So you're right that with every phase transition, the order parameter changes.
I have a follow-up question. So before this Higgs field, generated mass for all the quarks and leptons. So then, how can we even talk about mass before that? And how can we talk about?
So rest mass is zero. A particle's rest mass can be zero, but because the particles move about, their energy, because E is equal to mc square, whatever has energy E divided by c square will be the relativistic mass. So rest mass is zero, but because these leptons and quarks, they are highly in thermal state, they have high kinetic energy, so there is relativistic inertial mass associated with them.
So there's another question. Although there are many theories about CMB cold spots, but some people suggest that CMB cold spot is a result of extinction of the primordial black hole in that region. How does the extinction of a primordial black hole cause cold spots?
No, you see, the CMB's cold spots are okay. Here I must mention what exactly is measured. It is the delta T divided by T, where T is the average CMB temperature, which today is about 2.73 degree Kelvin. And but in different directions in the sky, the temperatures fluctuate, and the fluctuation is of the order of microkelvin. So delta T by T is of the order of 10 to the power minus 6. So some region is let's say 2 into 10 to the power minus 6. So that is hot spot. And some region may be having 0.1 into 10 to the minus 6. They are cold spot. So you might ask, what are the fluctuations due to? So the fluctuations are associated with formation of structures. That is, wherever the baryonic matter concentration was large, there'll be a particular fluctuation in the temperature. Wherever the baryonic matter concentration was much small, there'll be a certain fluctuation in the CMB temperature. And therefore, the cold spot can also be explained by what kind of structure formation processes were there. Primordial black holes, the kind of primordial black holes I am talking about, they radiate very high energy particle, while CMB is about at the microwave and radio waves. So therefore, the primordial black hole, which are evaporating, small black holes that are evaporating today, if such primordial black holes are there, which are evaporating today, they'll be giving rise to gamma ray photon. So primarily they'll be emitting gamma ray photon, and they can be indirect effects on the microwave background radiation, in the sense that just like in the case of Sunaev-Zeldovich phenomena with clusters of galaxy, if you have an ionized plasma, then because of the Sunaev-Zeldovich effect, the cosmic microwave background radiation going through such an ionized plasma, the effective temperature can come down. And so possibly what you're referring to is that if you have primordial black holes that are producing very high energy photons like gamma rays, X-rays, they can ionize the ambient medium and effectively decrease the temperature. So those are the indirect effects. I hope I have clarified the question that you have raised.
So there's another question, that creation of particle-antiparticle at event horizon, and the antiparticle is absorbed by the black hole. Can this cause more baryons than anti-baryons?
Probably the picture was slightly misleading. Look, in this process, like for example here, it is an electron which goes. That is a completely random. Sometimes an electron will go into the event horizon. Sometimes a positron will go into the event horizon. Because gravity doesn't distinguish particles and antiparticles, so therefore there will not be any net emission of matter over antimatter due to Hawking radiation, unless the gravitational physics itself is modified so that gravity starts distinguishing between particles and antiparticles. But so far, whatever we know about gravity does not favor matter over antimatter. That means in such processes, an electron can be swallowed by the event horizon, and so can a positron can be swallowed by the event horizon. So there is absolutely no bias towards matter as far as the event horizon is concerned. So it is very unlikely that a baryogenesis process can be generated purely through black hole physics.
Okay. Are there any more questions? Then you can either type or ask directly.
Hello, Professor Dasgupta. I am Hari Verma here.
Hello, 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 Professor
Yeah,
Verma.
it's a very interesting talk. So I have a very simple question. So when you mention about new physics, are we thinking about some new interactions or something else? When you
Well, the new physics was essentially associated with the question that was asked concerning the tension in the estimation of the Hubble parameter. Well, the kind of uh, ideas that I have regarding resolving the Hubble tension is not with new forces, but rather uh, using repulsive gravity that can arise, just like the dark energy which is invoked to solve the problem of late time accelerated universe. So, going along the similar lines, that whether new physics associated with sterile neutrinos causing anti-gravity, whether that can, in some sense, solve the Hubble tension parameter. So, of course, there is also uh, from certain experimental analysis concerning particle physics, people say that there could be a fifth force, evidence of a fifth force. Um, one doesn't know whether such a fifth force can ameliorate the Hubble tension. I don't know. I have not looked into the effect of the fifth force, which is speculated by some people whether they can help in solving the Hubble tension. So uh, I have not seen any research paper uh, which tries to solve the Hubble tension using the hint of fifth force that some particle physics experiments suggest.
okay, okay.
Okay. Are there
So
more questions?
feel free to ask any question, because uh, questions also trigger new line of thinking. It can also give rise to new ideas.
Girish, I think there will be no more question, I guess.
Okay. So, so yeah. Okay. Then let's thank Professor Dasgupta. So maybe there are, I think, two or three faculty members here. So maybe, and we can have some small interaction. So we request the students to then leave if they don't have any more questions.
Excuse me, sir. Can you hear me?
Yeah,
Yes.
yeah, I'm
Uh,
able to hear you.
yes, sir. Good evening, sir. Thank you for the wonderful talk.
Good evening.
Yes, sir. So what I want to ask is like I have a confusion in the that you have told about like fine tuning problem.
Yeah.
So, sir, there is like I have heard there is a flatness problem, like in which like we have a parameter which is fixed, which is like density of matter and energy in the universe. So, sir, in flatness problem or in like fine tuning problem, is there we have any reasons like why some parameters are fixed? So in flatness problem, there is density parameter who should be very close to critical density, and we see that this is very close to critical density. So is there any reason why we observe the critical density very close to one nowadays after so much times, like 14 billion years of expansion?
Yeah.
So
So the I don't know whether you have heard of the inflationary paradigm. So the inflationary models were created for the first time by Alan Guth and Linde and many others. Now there is a whole industry working on the inflationary paradigm. So inflationary models were invented to solve the fine-tuning problems associated with standard cosmological model. So you have mentioned one problem, namely the flatness problem of standard model. So for those who are not aware of this problem, let me mention what exactly is the problem. So there is a density called the critical density. If the total density of the universe is greater than the critical density, then our universe is closed, k equal to +1. If the density is less than the critical density, the universe is open. The value of k is -1. And if the density is exactly equal to the critical density, we live in a flat, spatially flat universe, that is k equal to 0. Now, you can ask, what kind of universe do we live in? That is, what is the value of k for our universe? If you measure the density of the universe through astronomical means, then you will find that the actual matter content, the standard matter plus dark matter content, is about 0.3 times the critical density. Okay, so it's not equal to the critical density, it's 0.3 times the critical density. So it is less. But then, does it mean that we live in an open universe? The answer is no, because there is also dark energy, but that's a separate matter. But what people like Dickey, Robert Dickey, who is no more, he is a very interesting character. He missed Nobel Prize twice or thrice. But Dickey, he had pointed out that suppose today our density of the universe is only 0.3 times the critical density. Then you ask yourself, what was the density of the universe, let's say during the QCD phase? That means when the universe was 150 MeV hot. You will find that the density, if today it is 0.3, the critical density, that time the density, the difference between the actual density and the critical density was divided by the density was less than 10 to the power minus 30 probably, or even less. That means the density in the past, when the universe was just born, was very close to the critical density, in order that today the density is only 0.3 times the critical density. So this is the fine-tuning problem. And how did inflation solve it? Inflation said that at some point of time, the universe expanded so fast, no matter what the k value is, whether +1, -1, or 0. But the universe at some point expanded so fast that today our observable part of the universe is a tiny fraction of the universe that expanded fast. So imagine, so to give you an analogy, that if our universe is a two-dimensional balloon, if the balloon inflates, that is, it increases in size to such an extent, then obviously whether it's k equal to +1, -1, 0 doesn't matter, because it has become so big that locally the balloon looks flat. It is like a plain sheet of paper. You will never see whether it is k equal to +1, -1, or flat. And that is how inflation solved this fine-tuning problem, flatness, also the monopole problem, because it expanded so fast. If there were monopoles produced, they got diluted heavily. And the other problem was the horizon problem, that why is it that cosmic microwave background radiation in one direction is exactly same as the other direction, although in the standard model, two diametrically opposite region, when the universe was very young, they would not have been in causal connection. But today the temperature is exactly equal. But in inflationary model, these two diametrically opposite direction, they are they come from the same small region that got expanded by sudden expansion, the inflation of the universe. And it is not a surprise, therefore, that the temperature is same. So inflation solved all the three fine-tuning problems associated with the standard cosmology. So I hope I have answered your question.
Yes, sir. Thank you. Sir, is there a direct observation of primordial black holes?
That's a very good question. Unfortunately, no. So there is no positive identification of any single primordial black hole candidate. And it is unfortunate, not just for the kind of baryogenesis work we are doing, is unfortunate. It was unfortunate for Stephen Hawking, because if a primordial black hole of low mass was detected, then Hawking radiation would have been detected and Stephen Hawking would have been awarded a Nobel Prize. So because so far there is no direct detection of Hawking radiation, the Hawking radiation is still in the theoretical level. Ultimately, all sciences, they have to be corroborated through experiments. So neither Hawking radiation nor primordial black holes have been corroborated observationally. So they are still at the level of theoretical analysis.
Okay, sir. Thank you very much.
Most welcome.
Okay, are there any more questions?
So I must apologize. There was some disturbance in between from the hotel, because of which at various time we had to sort of, there were interruptions. I'm sorry about it.
Yes, so that's perfectly all right. No issues.
Good to see you, Adesh. I think you're muted, so I can't hear you.
Hi, sir. How are you, sir?
Yeah, I'm okay. I'm now in Dubai. And
Okay.
yeah.
Yeah, sir. I heard some sad news.